All right, so before we go on with this problem, quick reminder. What are two things about an ideal pulley? If you see the words ideal pulley, that means number one, pulley is massless or nearly massless. And number two, the pulley has these bearings inside, so the pulley's bearings are nearly frictionless, or we're just going to assume frictionless. That says frictionless, believe me. Believe me. Frictionless. Yeah. Okay, so we have an ideal pulley Atwood's machine here. We're really good with these by now, right? Individual masses are, first of all, as soon as I see pulley, string, mass, all that stuff, forces. So if we're doing forces, draw free. I didn't say anything about that. If we're dealing with forces, first draw your free body diagrams, and then get your Newton's second law equations, and then solve for whatever it is you need to do. You can use system of equations if necessary, but we can also just treat this as a system, right? Let's get to it. External forces acting on the system. So here we go, 4 kilogram object. We know if we hit play on this little cartoon, the 6 kilograms is going to go down, the 4 kilogram is going to go up. So it's going to accelerate up while this one accelerates down. All right, so what's pulling the 4 kilogram up? That's the tension, of course. Slow down, Mr. Scapatis. We have boxes here, so that means it needs to be the correct size. So we're going to go up 1, 2, 3. 3 sounds good. And we'll call that tension. And then we also have the mass times acceleration due to gravity, like this. Can't be as much or more than the tension, because then you have a different net acceleration. Here, though, our tension is going to be the same thing, going 1, 2, 3, tension, and then the 1, 2, 3, 4 mass times acceleration due to gravity. All right, so let's do our Newton's second law equations next. So looking at the 4 kilogram object, the stuff that makes it go minus the stuff holding it back equals mass times acceleration. Uh, 6 kilograms, stuff that makes it go minus the stuff holding it back equals mass times acceleration. For the entire system, mass of the 6 kilogram times acceleration due to gravity minus mass of the 4 kilogram times acceleration due to gravity equals total mass times the total acceleration. Show your process for solving for the systems of acceleration and the tensions in the string. Okay, so just by using this last equation, are we given the acceleration? We have free to draw a free body diagram, then use each writing equation, external forces. No, so it looks like we're going to just solve this equation for acceleration. Okay, so I'm going to use this equation right here. And I'm going to go ahead and use my numbers because you guys are good. So the 660 minus 40 equals 10 times A. So that's 20 divided by 10 equals A. A equals 2 meters per second squared. Cool. So now that I know my acceleration for the entire system is 2 meters per second squared, now I can take this and I can go ahead and plug it in to solve for tension. And I'm going to just plug it in here. I'll change colors so you know we're doing something a little bit different. So this is the 4 kilogram. So I'm going to add my mg to each side. And I'll rewrite the equation, T equals MA, so 4 times 2 is 8 plus 40. My tension is 40 newtons. Okay? Now, suppose an additional mass is added to the left, so the left-hand side is now 5 kilograms. So we're adding on an extra mass, or we're adding on one of those little cylinders, or clipping on a hanging mass to the bottom. How would this change the acceleration of the system and the tension in the string? If we do that, if we add in that extra mass, that means when we combine total masses here, where did we combine total masses? Right here. When we combine those total masses, then this becomes a larger number. And remember, this 10 right here was the combined mass previously. So now this 10 becomes 11. Well, what happens when you divide by a larger number? That would mean your acceleration will go down. That's not how you spell acceleration, it's silly. Acceleration is going to go down. And what about your tension? Tension is therefore going to increase. So come back to this free body diagram. If we're adding more mass here, then that means this is going to become larger. Well, our tension has to be more than the total weight going downwards, because remember, we're accelerating upwards. Yes, with a smaller amount, but we're still accelerating upwards. So you have to have a net upward force to pull up on that mass.